Good morning, everybody, or good afternoon. We just had a little hiccup there trying to get online, so we'll just give it another couple of minutes just to let everybody in. Okay, I think we'll probably get started. If there are some stragglers, that they can jump in. Well, thank you very much, everybody, for joining us this morning on our last day of 5 masterclass presentations. This morning we've got Will Twigg from Simply Ventilation and Alleviate Acoustics, and he's going to tell us all about building a quiet life. During the presentation, if you have questions, please do log them into the chat, and then when we get towards the end, I'll ask Will to respond to those, if that's all okay. Okay, Will, I'm going to stop sharing and I'm going to hand over to you.
Thank you. 2 seconds. I think this. Can you see that, Steve?
Yeah, that's all good. Yep,
Cool.
Good to go.
Thanks, Steve. Good afternoon, everybody. As Steve has said, I'm doing a little presentation today on touching on some general principles of acoustics, sort of broad brush over some noise control methods, attenuation and the likes, and how clever design in building services and buildings could promote good acoustics in buildings. So sound and noise, which is which? I think this is a personal choice, really. What everybody perceives to be noise, and what everybody perceives to be something that's acceptable, so an acceptable sound. By definition, sound is a pressure variation we pick up in the air, so our ears pick that up for us. And I think the definition for noise is probably something that's unwanted, irritating, or annoying, and something which is highly subjective. Now, the speed of sound is about 1 mile in 5 seconds. There's a little question at the bottom there, specific really to building services. Take that fan as a little example. If the air blows left to right on this fan, is the noise heard on the inlet? Now, this is one I'm going to answer. It's something I get asked all the time. Well, it's an extract fan and it's blowing out of the building. Surely I don't need a silencer or noise control on the room side because the air's blowing the other way. Well, in fact, albeit quieter, the noise does radiate down the duct from the fan the other side. So we'll come on to a little bit more about that. Two terms, sound power and sound pressure, commonly used, commonly seen in acoustic reports, building services. What are these? So sound power level is energy. So it's the energy rate of a particular unit. That may be a fan, it's any noise episode, and that's its source level. So it's total noise level produced in all directions. Sound pressure. So this is what we pick up as humans. So the human ear picks up. And that is effectively a sound power level at a distance. So a sound pressure level may be an NR level, a dBA level. We'll come on to those shortly. But it's something which has been affected by characteristics of a space and also distance. Convert this into a heat analogy. So imagine an output of a heater in watts. That will be in acoustics a sound power level, and then a temperature. So a temperature perceived in a space would be a sound pressure level. And obviously the sound pressure level, or the heat and the temperature in the space, that's affected by the starting sound power level of a unit, but also the size of a room and the characteristics of that room will determine the overall sound pressure level or noise level within the space. So the decibel, named after Alexander Graham Bell. Why was the decibel scale introduced? Well, the reference level for sound power is watts and sound pressure is pascals. And as you can see there, different noise episodes going from right the way down to extremely quiet all the way up to extremely loud. You can see that in watts and pascals, it becomes very difficult to manage. So the decibel scale was introduced to be able to give it a manageable scale that we can work with, and give sound power and sound pressure a common reference, being the decibel. Now we'll come on to it later, but sound power and sound pressure aren't the same thing, albeit when it's in decibels, it's presented as a decibel to give us that, functionality, allow us to work with the numbers a little bit easier than watts and pascals. As far as levels are concerned, we'll come on to what we can pick up as humans, but noise can actually kill us. So anything above 150 decibels can almost destroy your auditory nerves, ringing in the ears, and higher than that is something that's going to be incompatible with life. So what is a decibel? It's a logarithm ratio of two quantities, which is why it allows us, although the calculation is different with power and pressure, it allows us to come up with a common reference, so decibel. Now, you'll see there that two calculations in reference of a sound power and sound pressure equal 90 decibels. What's very important is that power is not equal to pressure. So a source level of 90, so a power level of 90, is not equivalent to a pressure level of 90. And particularly in building services, manufacturers' data, how this is presented on data sheets, you often get people presenting power as pressure and pressure as power, and maybe not picking up the differences between the two. So it's very important that it's clear. And you'll often see SWL or LW, and that W being the reference to watts for sound power. And also sound pressure level, you may see that presented as SPL or LP, that P being the reference to pascals that we saw on the table before. Now, our audible range, we split noise up into different frequencies, low and high frequency. Low frequency very much being bass tones and rumbles and things like that. And the opposite end, high frequency, so high pitched whistles, hisses. And as humans, our audible range is about low frequency from about 20 hertz up to high frequency, sort of 20,000 hertz. But as we get older and as our ears deteriorate, that high frequency element of our hearing does start to reduce over time. So levels, particularly seen in building services, NR levels, an NR curve. So this is a sound pressure level. It's just one way of measuring noise levels, particularly inside buildings and from services. What an NR level is an equal loudness contour. So it's a reference point across the octave band 63 hertz through to 8,000 hertz, and a measurement is taken in each of those frequencies and plotted against a curve to determine what NR level is being measured in that space. Now, specifications on projects and in construction often have acoustic reports, but there's times when sometimes there's not a noise level specified, and CIBSE Guide A is a good reference for this, and CIBSE Guide A uses NR levels. It's a useful tool to get a bit of a guide on what sort of noise level you should be using on a particular project. And also HTM 0801, so healthcare, this also adopts NR levels. So again, they use NR levels as a specification in various different types of rooms on a project. How do we work out an NR level? If we wanted to know what a particular space was in terms of an NR level, all we would do is measure the noise level in each of the frequency bands, 63, 125 upwards, and plot that on the curve. So you can see this little example there. The line in red is the measured pressure level in each of those frequencies, and the highest point of the curve you'll see sits just on NR38. So that particular example would be NR38. Now, if any part of that measurement, any part of that curve exceeded the NR level, it would mean that that NR level would not be achieved, unlike a dBA level, which we'll come on to on the next slide. Often asked, what's the comparison between dBA and NR? Albeit they're two different things. One's an average single figure and one's a spectrum. Roughly speaking, the NR level is circa dBA minus 5 to 7. So if you had a level of 40 dBA that was measured, it would be roughly NR 35. So coming on to dBA, again, a dBA level measured in a space is a sound pressure level, just as it was with the NR level. However, it's an average over a period of time. So that dBA figure is a combination of all the frequencies, 63 to 8,000 hertz, all combined into one single figure. What that A means, you'll see that A on measurements, you'll see that A on manufacturer's data. That A is a weighting correction. So it's the A weighting correction. And that's to compensate for our ears' poor response to sound at low frequency. So if you ever see that A on manufacturer's data, that means that figure will be A weighted. And this must be accounted for in calculations. If anybody ever does a calculation for noise control, attenuation, for example, this needs to be accounted for. And some manufacturers present their figures with A weighting and others without, so linear, so unweighted. And it's really important is that A, because it could send the calculation, hugely out if it's not picked up on. So just a little example of how you get from a spectrum, so a measured pressure level, down to a single figure. So you'll see there, as we did on the previous slide with the NR level, we have a measured pressure level at each of the frequencies, 48, 44, 43, etc. We add the A weighting correction to give us a resultant weighted curve. What we do then is we add these up in pairs. So we'll add 22 and 28, 34 and 37. And the table on the right there, with acoustics and with decibels, it's all dependent on how the two figures compare. So you'll see there, if the two figures were between 0 and 1 of each other, you would add 3 dB. So what that means is if you have 30 dB and 30 dB, that would equal 33 dB once added together. So we do the same thing to get down to our single figure dBA at the bottom. And this particular example is 42 dBA NR38, as was on the other slide. Now, particularly in external noise, external acoustics, and when limits have been set on plant items or a project-specific limit has been set by an acoustician, they often say in a report that the noise levels from plant or the building has got to be 10 dB below the existing background level. And you see there at the bottom of that table, 10 and above adds 0 dB to the overall level. And that's really why acoustic consultants and local authorities are wanting you to be so far below the background level, is so that you don't increase that background level with new items of plant that might be installed. And what's important to consider is once you add a spectrum together to get an overall dBA, there's no way of reversing that process because you don't know which frequency is dominant like you do with an NR. So once a curve's been added to get a single figure, you can't then reverse that process. NR and NC. NC is a less common building services criteria used, but again, it is seen from time to time. An NR level was developed, is a European reference. NC was developed in the USA, and sometimes it's carried over in specs in this country. While the NR is slightly more stringent at high frequency, they are basically the same thing. So NR35 is as near as damn it NC35, but again, it doesn't come up that often. It's rarely used, and NR is far more common. in this country. So what control methods, noise control methods do we have, particularly in ventilation and building services? The most common, without doubt, is attenuators. What is an attenuator? It's effectively a section of ductwork with internal splitters which are packed with rock wool, and that attenuator absorbs noise at varying different frequencies and varying different performances. Now, it's important to consider that there's thousands and thousands of permutation of attenuator, each with their own subtleties, their own configurations, which affect different frequencies of sound. So when it comes to attenuators, saying, oh, I'll have a 900 long attenuator on my building services system, there could be 25 or 30 options at that particular size. So it's very much picking the right one for a particular application. And attenuators are often used between rooms to prevent speech interference. You know, the term being crosstalk attenuators, but actually, despite what some people think, a crosstalk attenuator is just a name for an attenuator in a different application. So there's nothing different from a standard main plant attenuator than there is a crosstalk attenuator, other than probably its size. So the inner workings of an attenuator, how does it work? Absorbs sound and absorbs and converts that into minuscule amounts of heat, so nothing that's ever going to be noticeable. And we often add central splitters into attenuators to affect the performance. Now, obviously, what that does is introduces pressure drop into the system, so that's a balance, not introducing too much blockage in the airway. And by adding absorption, by introducing more splitters, gives the sound more lining to collide with, and ultimately improves its performance. Now, you can adjust the splitter thickness to change its characteristics. The thinner splitters, more number of thinner splitters would give better high frequency, better absorption, whereas thicker splitters would give better low frequency because of their overall mass. So often the case in buildings is a very small plant room and a bigger than anticipated attenuator. Appreciate things don't always go ideal, and often a building's designed before the services engineers may get involved, or particularly get involved to some detail. And the amount of times we get asked, oh, I need an attenuator, I've only got 600 mil, or I've only got 900 mil of space. It's really, really, really important to allow sufficient space for attenuators. And while a ductwork velocity of 6 meters a second might be acceptable from a design perspective, from an attenuator perspective, it's not very good, and it's difficult for us to get selections with reasonable performance and reasonable pressure drop, which is why often you'll see attenuators bigger than duct size, transformation pieces. But ultimately what this is going to mean is bigger plant rooms to ensure you're going to be able to fit those attenuators in prior to ductwork exiting out. So some other noise control solutions. Acoustic louvers. Acoustic louvers are a good option, probably more so in screening plant items or replacing holes in walls where an increased performance might be required. The problem with acoustic louvers is their free area. So the free area of an acoustic louver typically might be around the 30% mark, which obviously means that particularly if used and required for specific airflow purposes, is there's a sweet spot to achieve a reasonable pressure drop. With very high velocities, acoustic louvers don't tend to work, as the pressure drop will just increase hugely, way above 100 pascals, which often doesn't become practical. So they're good when used in the right application, and obviously depth-wise, a shallower 150, 300 or 600 mil. So they're shallower than attenuators. However, the pressure drop and free area is often the critical element of it, which may sort of dictate whether they can be used. Another noise control solution, acoustic enclosures. So basically an acoustic enclosure is just a bespoke item. It might be a combination of attenuators, panels, acoustic louvers generally speaking, used for chillers, heat pumps, or condensers where they may be located particularly close to residents or housing. And as you can see there, that picture in that example, that was a small heat pump system with intake and discharge attenuators. So the actual heat pump itself was fully enclosed in a panelled enclosure with intake and discharge attenuators to suit the requirements. Acoustic screens. So acoustic screens could come in two forms. That might be a solid panel screen with an absorptive inner, or it might be an acoustic louvered screen. So, you know, louvers can be made to suit a screen in any size, any active of plant and any height. So it's effectively just adapting standard products to work within a screening system. And screens are particularly good if you've not got a huge requirement for noise reduction, but obviously the top of an acoustic screen might be open to get air in and out of that enclosure. So it's good for better from an airflow perspective in getting air in and out of an enclosure rather than in and out of an enclosure, and can be used in, you know, louvered or solid panelled screens. Some other sort of little bit different noise control options, inertia bases. Now, these are manufactured generally for pump sets and things in plant rooms where vibration might be a problem, and effectively it's a solid base which might be mounted on spring hangers to deflect vibration if say a plant room is particularly close to a noise sensitive area. And again, vibration isolation. So vibration isolators, spring hangers, you might see them called, often fan coil units, heat recovery units, chillers, things like that are all may all be sat on spring hangers. And again, all this that's more vibration, really, and all dependent on weight and the required deflection. You may have an air handling unit or a chiller sat above a low critical low noise lecture theatre, for example, which needs vibration isolation to deflect the vibration from that plant so that it's not picked up in that space. And again, just another adaptation, really. Heat pumps are obviously becoming very popular, and that's really an ongoing. You know, we've got standard products for chillers, and because these things are getting, you know, replacing old redundant plant or refurbishments, you know, commonly they may be situated close to residents. If people are replacing old plant items in a plant room with an external heat pump, obviously from taking something inside to outside often needs some additional noise control. In this particular example, you can see on the right hand side was a chiller with intake acoustic louvers and a discharge attenuator on the top, so that obviously the air is split up from the intake to the discharge, and again of varying different performances. So how does the location of services in buildings affect acoustics? Now, we've touched on the previous slide that small plant rooms might not mean sufficient noise control can fit. Take this particular example, an assembly hall. It could be anything. NR30, a fairly quiet noise level required in the space. Attenuators, ideally in any situation, want to be within a plant room prior to noise being able to escape out of that plant room. In this application, you can see that there's very little space in that plant area, very little space for any attenuators, and therefore the attenuators are situated outside, already in the assembly hall, and the room being served. The problem with that is noise has potential. It'll always have potential to get out prior to attenuators. So any transformation pieces, any ducts, unattenuated ducts through walls, it'll always break out of those ducts and find a weak point, and particularly transformation pieces being particularly weak from an acoustics perspective. So in that particular example, the plant, in my opinion, is way too close to the space. Is this done for value engineering? Who knows? It may be done for other reasons, but in this particular application, the attenuator should be in the plant room, out of the way, the HU attenuated at source. So ultimately, a bigger plant space required. Can plant location affect acoustics cleverly without really the need for noise control? The answer to that is yes. Distance has a big effect on noise levels within a space. Take this example of a lecture theatre. Purely the seating arrangement would mean that the plant item, or the main plant item in the air handling unit, is situated further away. So obviously you've got your grills, which might be a couple of meters from somebody sat down in that space, but the plant item itself is 4 meters away in that instance from the nearest receptor. That 4 meters, while it may not seem much, and standard height of a ceiling of 2.6 or 2.7 in a normal space, you may think, well, is that going to make a massive difference? But sound decays massively over distance. So just changing from 1.5 meters to 4 meters away from that plant louver would make a big difference on the perceived level within that space. And this is applicable to many types of spaces. Sports halls, swimming pools, where you may have a big louver on one end of a swimming pool or the other. And cinemas and theatres, where can the plant item be positioned to give us the best chance of achieving a noise level within that space? Here, if we flip that application around, where the plant room is located to the rear of the lecture theatre, what can be seen there is that extract louver is very, very close. We don't have that distance. We don't have the benefit of the distance anymore. And in fact, that may be just 1 meter behind somebody. So that change in distance may be the difference between requiring a 1200 or an 1800 long attenuator. So distance itself can have a very big impact on the required noise control for a space. How can building services engineers help alleviate noise problems? Often it may be taken out of a services engineer's hands. An architect may require a project, or a client might want a project to be exposed services. This makes things difficult when it comes to acoustics, particularly in an application, for example, where we've got multiple fan coil units in a space. How are we going to achieve an NR level that's specified without a ceiling helping us out from a noise perspective? And while a standard fibre tile, laying tile grid ceiling might only give us 2 or 3 dBA reduction, that 2 or 3 dBA reduction may be the difference between us achieving a noise level in a space and in fact not achieving a noise level in a space. Now that then comes down to the service engineer's job of selecting the plant and ensuring that the manufacturers are considering the fact that there are no ceilings. How might this affect the selection? How might it affect its location? Ultimately, how might it affect its running speed? A fan coil unit might do a duty on 3 different sizes, running at 3 different speeds. But what's very important is ensuring it's selected on the correct one for the particular noise criteria required. If you're working with manufacturers of kit, always request a guarantee. Ask them if they're comfortable that the level's going to be achieved as a whole. Often manufacturers' claimed and actual levels can be very different. Take the fan coil unit example, continue that example on, and the industry has a habit of using what they call guide NR. So guide NR being assumptions of installations. That might be an assumption of distance between fan coil units. That might be an assumption of ceiling types. That might be an assumption of reverberation. But ultimately, it's an assumption and not an actual. So it's very important to ask manufacturers if what they're providing is going to be the actual noise levels that are achieved, because claims and actual levels can be very, very different. And again, the types of space. So is a space highly reverberant? So is there a big office with lots of glazing, hard surfaces, not very much absorption? And that's got to be considered as well. That'll make a big effect on the overall level perceived, and make NR and dBA levels and the compliance of those quite difficult. So we touched briefly on it before. Attenuator positions. How will that affect us in achieving compliance? As I said at the bottom there, you quite often may not have the luxury to decide on this, but the top one being a perfect example of the attenuator, which is downstream of an air handling unit, and all that ductwork between the attenuator and the unit gives the opportunity for noise to break out. So in a plant room, that might not be a problem. A louder plant room might not have an issue. However, what that might mean is that if that duct was over a space, for example, so if that duct was running over a lecture theatre or a ward area in a hospital, that noise has the potential to break out before the attenuator. So it's effectively an unattenuated duct. So it's that balance. Putting the attenuator close to the air handling unit, ensuring that your duct's attenuated prior to it passing over a space. And again, as we've said, maybe don't have this luxury, and sometimes it's a bit of a balance between achieving the two, hitting a sweet spot and making sure that the service is compliant within the space that you've got. Again, take another example, an air handling unit in a plant room. That duct exits the space. It's got a bend section before it gets to the attenuator, and that attenuator is within the office. So again, all these things, fire dampers in walls, dampers, detail around construction of a wall, all these elements have an impact and have a potential for noise to break out or noise to flank round out of the plant room. So where the blue might pass through the wall, you know, often acoustic insulation or lagging is actually required, which is not only expensive but also very heavy and difficult to install. And that might actually be required from the point that duct enters the space right up to the quiet side, so the end of the attenuator, to make sure that noise breaking out of the ductwork is not going to be a problem. I get so many calls, your attenuator is not working, can you help? Not saying that people don't make mistakes, and we don't make mistakes, but often installation is a big factor in noise control and noise problems. One which I've seen all too common is airflow onto grills, over OBDs, onto plenum boxes, and acoustic flex. And acoustic flex obviously has its benefits, has its reasons why it's got to be used. Now, a top entry box with a squashed acoustic flex onto the back of an OBD, as you can see on the left hand side, can make air become very turbulent. An attenuator can do the best job in the world, but if you get to the grill and the installation and the flexible squashed onto the back of the grill, the attenuator can do what it wants, but you'll still have a noise issue because the air is so turbulent across the grill. On the right hand side, take another example, and again, this might not all be practical with ceiling void depth and things like that, but you take the one on the right, a nice smooth transition onto a side entry plenum box, gives the air the chance to stabilise prior to it going across the grill. So while it's very important to ensure grill selections are low noise and OBDs are set correctly, the installation and the grill box and the flexibles onto the grill can make a massive impact on the noise level and creating high velocities and whistlings across the grills if it's not done properly. Recommended ductwork velocities. Now, recommended ductwork velocities from a services perspective and recommended ductwork velocities from an acoustics perspective may differ slightly. We always try and relate the velocity in a duct to its position. So is it a riser, is it a sub-branch, is it a grill, etc., and against the noise criteria. Obviously, these are rough, these are rules of thumb, so to speak, but basically the further down the system you are and the lower noise criteria you're trying to achieve, then the lower velocity you require. Obviously, if you imagine a final duct to a grill being very high velocity, there's nowhere in that system for that velocity to reduce, and it's at the last point, and you're going to pick up a lot of velocity noise across a grill and grill box if the final duct to that grill is high velocity. So it's critical in services, particularly when you get down to NR20, 25, cinemas and lecture theatre type levels. It's critical that the velocities are kept very, very low. The attenuator pressure drops are kept very, very low to make sure that there's no regenerated noise in that system, which would potentially compromise the level in the space. How are attenuators tested? Obviously, data for attenuators is critical in ensuring that attenuators are put forward which are compliant. ISO 7235, the latest version being 2009. This really ensures that anything that's claimed is tested. So if anybody says that they've got products that are not tested to 7235, I'd stay clear. But it effectively allows manufacturers like us the ability to test. The picture there of the test rig at our factory allows us to test bigger, smaller, and in different configurations, sizes of attenuator, so that we understand very well the effect of different configurations and different sizes and lengths, so that once we get asked to provide a product with a specific insertion loss, we know that that insertion loss we claim is actually the insertion loss which is achieved. And in doing so, attenuator testing and ISO 7235, that picks up a static insertion loss, so an insertion loss without airflow, and a pressure loss. So obviously we want to know what the pressure drop is across that attenuator. And again, like we touched on the last page, while attenuators are there to reduce the noise, if we're not careful, we can actually generate noise. So we can create noise, or sometimes its definition is flow noise. So by putting an attenuator in a system that's high performing, high velocity, high pressure drop, might leave us a little bit stuck when it comes to undoing the job of the attenuator in the first place by creating a lot of regenerated noise. And that comes down to attenuator positions as well. We always advise straight runs of duct either side of an attenuator. Attenuators shouldn't be, if at all possible, positioned after or before bends, because all the testing we do is all based on laminar flow conditions. So if we claim a pressure drop of an attenuator to be 25 pascals, for example, that's 25 pascals laminar. And although we can correct that on site, if that's wedged between two ducts in a very, very tight space, the likelihood is the pressure drop of that attenuator measured on site is going to be much, much higher. So just the last few slides, some considerations when it comes to building services design. I've got a crosstalk attenuator here as an example between two spaces. Is my system protected? Have I put a crosstalk in that system? Is there anywhere in that system where I might need crosstalk attenuators? And often crosstalks are there to maintain the privacy between rooms, but also maintain the performance of the partition which it crosses. That particular example there, you can see two extract bell mouths with an attenuator positioned over a partition. Now, in doing so, putting a standard attenuator in there with no consideration to the partition, we don't know that that's going to achieve that. So that attenuator, that crosstalk, must maintain as a system the overall performance of that wall. From services engineers' perspective, has the architect on the project provided a wall performance? Have they given a wall drawing? If not, is there one? We can select crosstalks to maintain, as rules of thumb, maintain speech privacy. But if there's a wall partition to maintain, that may result in a much bigger attenuator. So it's important to always check that is if there's a wall performance specified by the architect. The installation, we touched on the installation of grills. No different really with this crosstalk. So is the installation detail in accordance with recommendations? So an acoustic consultant will often give you in their report specific details of how ducts should be installed across walls, how dampers and attenuators and the likes. Because again, like on the previous slide where we talked about attenuators there to reduce noise, But if you've got a poor installation, the attenuator can do all it wants, but if there's gaps around that and the installation's been poor by the builder, ultimately these failures with crosstalk generally come down to poor installation on site. Room acoustics. May have heard the term reverberation. Now, a reverberation time is the time it takes for a noise level to decay within a space, and that's in seconds, so it's 0.5, 0.6, 0.7 of a second. But ultimately, it's how reverberant or how absorptive on the flip side is that particular room. Now, while as service engineers we may not be able to influence that massively, an architect working hand in hand with a services engineer is or an acoustic consultant, for example, may be able to consider that reverberation time a little bit more. How might our system affect that noise level? So we touched on before, fan coil units been exposed in a space. If they're exposed, a local fan coil unit system is naturally going to have a higher noise level than a dedicated main plant system. So what can we do to reduce the reverberation time, or on the flip side, increase the absorption within that space? Rafts and acoustic tiles. Could we put rafts below any local plant items, fan coil units and heat recovery units to effectively mimic a ceiling? And while there's often exposed services, often they're not. Nowadays, there may be part ceilings, rafts under things, and different details. So can these be coordinated with the services engineers so that any noisier items of plant, such as fan coil units and heat recovery units, can they be placed above those rafts or those ceilings to help us give us a fighting chance, really, of achieving an overall noise level? So the plant location, can it be moved? The initial answer to that question in most cases is probably no. But does the plant location suit the acoustic strategy? So take that example on the right with 2 air handling units on a roof at a hospital in Birmingham. Where is our nearest noise sensitive receptor? Is our nearest noise sensitive receptor within the hospital? So is it another ward bedroom, or is it an office that's very close to the openings of the air handling unit? And could a small change in plant location save further costs down the line? So direction has a big impact. So what we call the directional effect. So could a change in direction just by 45 or 90 degrees, so could those HUs be flipped the other way around, pointing one way or the other? And that might make in itself a very noticeable change in the overall noise level of the receptors. So if your house or an apartment was in direct line of sight to an air handling unit, for example, could just changing that air handling unit to flip that round the other way, turn it around away from the receptor, is that possible to help mitigate any further noise control methods? Multiple plant items. Acousticians will always consider this, but could plant items be split up? Is there multiple plant areas, or is there multiple ends of the building where plant items could be positioned? Has this been considered? So putting large items of plant all together in a plant area is very common in building services. It's often the way to go. Let's put our plant in a single area, a single plant room, a single roof space. But is there potential to move some of that kit? Is there potential to keep that noise level down on the roof so that overall we've got a fighting chance of hitting the requirements regards to noise? A little bit early, Steve, but it'll give us some time for a few questions if anybody's got any.
Yeah, well done, Will. That was a really fantastic presentation. It gave us all an indication of the very first principles for building services engineering. I had a little shudder when I heard the word reverberation. I remember doing a project, and it was a school, and the guy from BRE was really keen on reverberation. When we walked into the sports hall, he clapped his hands and then looked around and he said, "Oh, that's not too bad. It's about 0.8. Now, how we managed to just do that, I'll really never to this day know. While people are just putting some questions up, I've just got one or two myself, and I think Henry's got one chipped in there. The sizing of attenuators, I think you made a really good point there. I mean, one of the things that I see with young engineers is that when they draw the ductwork up, they put the air handling unit on, and then they'll just put a line size AHU in, too short, and you can never fit it in. And then they go away, design everything, and it all goes wrong. I think that's a really good, valid point for people to take away. I think the other thing on sizing of attenuators is the pressure drop. Because as consultants, often we will design a system that will have maybe a silencer with 20 pascals, and then when the contractor gets it and then they relook at that, they reduce the size of the attenuator to save money, but the PA, the pascals goes up, and all of a sudden everyone's scratching their heads because the system's now not performing. Now, Henry has asked a question about can crosstalk attenuators compromise the fire engineering strategy? Now, I think he's probably referring to the diagram that you had up where you're showing the attenuator right in the middle of the wall.
Yeah.
Do you want to answer that question?
Honest answer, yes. I think the way around that, from an installation perspective, crosstalks don't have to span the wall. So obviously, if you've not got a firewall, particularly in that instance, while it's maybe not good practice in that particular example per se, but the workaround would be to have a fire damper in a wall, have the attenuator one side of the wall, and so long as the grill is prior to the attenuator, i.e., there's no chance of noise getting into that duct prior to the attenuator before the wall, then there's no reason that attenuator, a crosstalk can't be one side of the wall or the other. So yeah, I think the workaround is a fire damper.
Yeah, and there's no reason why you can't add, acoustic cladding over between the damper and the actual attenuator. Yeah. If that's potentially a risk. You mentioned on an early slide that the linings in an attenuator being made of rock wool. Is that consistent with most attenuators, or are there alternative materials?
No, I think the only thing really that probably fluctuates from manufacturer to manufacturer is the density of rock wool. So obviously different densities of rock wool perform differently in terms of the frequency and the reduction that gives. Some manufacturers will use roll type, so they'll use effectively loft insulation. So what's in your loft at home, so less dense insulation. Others will use slabs, so square slab, much 40 kg density. So I think rock wool's used in all attenuators. I think the only thing that changes really is its density.
And what about the risk of fibres passing out from the rock wool into the space? Is that an issue?
Yeah, so hospital systems, particularly a good example. We always put Melanex lining, so that's just a little plastic. It's almost like cellophane on the front of the splitter. What that means is there's almost zero chance of the rock wool shedding and coming out of that, coming out of the attenuator. I mean, they do have a scrim facing on them as standard anyway, but that's fibre. So by wrapping them in Melanex, it just makes that watertight in terms of fibres not getting out to clean spaces.
Okay. And I think just one last question for me, and I'm not sure there's any more on the chat. You mentioned noise and vibration. And often these two things are kind of joined together and are perhaps separate as an issue. But I mean, in terms of the sort of the anti-vibration mounts that you're showing there, presumably that's to reduce the vibration and therefore the vibration generated noise from the machine. Is that the purpose there of the AV mount?
Yeah, correct. Yeah, and I think most it don't tend to be that common because all fan manufacturers tend to mount their fans on anti-vibe. So if you get an air handling unit with a fan in it, the chances are that fan's mounted on some sort of anti-vibration anyway. So the need for any further anti-vibration tends to come on very, very low noise criteria spaces, TV studios, or low critical lab type spaces or things like that, microscope rooms. So it's few and far between, but while it's not looked at commonly, it's used very commonly in fans and fan manufacturers mounting their fans on springs. So yeah, it's just basically to deflect any vibration, so there's no vibration noise perceived in a room below or adjoined to a plant area.
All right, we've got a couple of questions. Jack Beach is doing, it seems, a very studious project. He's asked, would you recommend any velocities to use if designing a system to NR15?
Yeah, NR15 is very difficult. NR15, you probably want your main duct runs to be no more than 1.5 meters a second. Final distributions to grills below 1 meter a second, which in turn will give the attenuator. I mean, it's all a function. So the attenuator pressure drop is driven by velocity and configuration of the attenuator. But yeah, NR15 is very much everybody working together correctly and everything going perfectly right. Otherwise, it's a tall order is NR15. So velocities are going to be
fast,
very low. Yeah,
I agree. Henry has asked the question, what are the cleaning instructions for attenuators? Is this required?
So cleaning generally in accordance with ductwork cleaning. Obviously, it makes it a little bit more difficult. Attenuators should always be installed with access doors either side, or at least access available to that if it was bolted to an air handling unit, for example. I think this question particularly comes up with kitchen extract systems and grease. And attenuators are a perfect place for grease to settle on. And I think a lot of people, cleaning in accordance with TR19, it's very difficult to encompass a full system, and having adequate access either side to be able to physically get down the airways of an attenuator. But in terms of actual cleaning, just non-abrasive solutions and soap and water, basically. It's nothing fancy required, and there's nothing that can really damage that attenuator unless you use particular harsh chemicals.
Yeah. Okay, well, that's been brilliant, Will.
Right.
We'll probably wrap it up there. Thank you very much for that presentation.
No,
for those listening, the presentation has been recorded and we'll give you a link to that, and I'm sure we can make the slides available to you. This has been the last of our 5 days of masterclass. For those who have participated in the previous ones, I hope you've enjoyed them all, and I'm sure we will be back again next year, and I think we'll just close it down there. Thank you very much,
everyone.
Will.
Cheers. Thanks,
Cheers.
Bye-bye.